In this module, we shall be discussing about the disturbance term in the simple linear regression model. We all know that there is a presence of an error term which affects the dependent variable. So whenever we are going to do the testing of hypothesis of any of the parameters, whether it's alpha or beta, we have to also consider the presence of this random term or the error term or the disturbance term, which is considered to be epsilon. And in order to address this error term, we have to go for a proper testing procedure. So this basically goes back to the testing of hypothesis for the disturbance term. And this disturbance term is incorporated within the variance of the estimated slope coefficient, or also within the standard error of this estimated slope coefficient, and thereby it affects the testing procedure. So in order to discuss on this error term or the disturbance term, we go by the particular variance of beta hat. All of us are aware about the fact that beta hat is basically the estimated value of the slope coefficient in a classical linear regression model. So whenever we consider the variance of the beta hat, it goes by sigma squared by n. But in this particular slide, we observe that instead of only sigma square, it's written sigma square u. This sigma square u is actually very important because it is referring to the sigma square of the disturbance term or the error term, which is u, and that is corresponding to the error term. So we want to say that the variance of the parameters, whatever we find out, is directly proportional to the variance of the disturbances. That means if the sigma square u is on the rise, then the variance of beta hat also will be increasing, and so sigma square u also plays an important role in this testing procedure. And so we can see that sigma square u has to be taken care of, or it has to be incorporated within the testing process. So this goes back to the properties of the beta hat, which has already been taken up under the ordinary least square regression. So we go to the properties of the beta hat. We say that beta hat follows normal distribution. So n for normally distributed, which is having the population parameter beta, because this is the sample mean, or this is the expectation of the beta hat equals to beta. Because according to the blue property of the beta hat, it is known that beta hat is an unbiased estimator of the beta, and so beta hat is unbiased. That is why it's written beta, comma, sigma square u divided by summation of xi square. This sigma square u is the variance of the beta hat, and sigma xi square or summation xi square is in the denominator, which calls for the sum total of observations. So here we observe that beta hat is normally distributed with the mean of beta, because we know that it is an unbiased estimator, comma, sigma square u by summation of xi square, which is the variance of the beta hat. So given these two properties of the beta hat, we can proceed for the testing of hypothesis of this slope coefficient, taking care of the variance of the disturbance term. So in order to do that, we define the z statistic. So by the z statistic, we mean that beta hat minus expectation of beta, because beta hat is the estimated slope coefficient, minus expectation of beta is the slope, or it is the mean of the beta, divided by standard error of beta hat, because this is according to any kind of statistic which is there in the testing of hypothesis, which means the sample estimate minus the population parameter minus the standard error of the sample estimator. So this sample estimator is in the denominator, which is considered to be sigma u, which is the standard deviation of sigma square u, root over of 1 by summation of xi square, because we know sigma square u by summation of xi square and the square root is being considered. So this comes up as the z statistic, and we observe that it follows n0, 1. So when I call for n0, 1, it means that it has a zero mean and a constant variance or variance 1. So that is how the underlying normal distribution of this particular Z statistic. This goes back to the properties of the beta hat, which goes for normally distributed with the mean of beta and variance of sigma square u by summation of xi square. But this has to be taken care of that the variance of the disturbance term is known. But under real life or in the real life domain, we will see that this is basically unknown. So if it is unknown, we have to estimate from the sample. So from the sample, we go for summation of ei square by n minus 2. So this ei is basically the error of the sample, which is considered to be summation of ei square in the numerator divided by n minus 2, which means n minus 2 degrees of freedom. So this n minus 2 is basically number of observation, which is n, minus the two parameters which are to be estimated. So given this expression, we can see that sigma square u is unknown, and so it is estimated from the sample as it is given by summation of ei square divided by n minus 2. So this basically goes back to the Z distribution, where instead of standard error of beta hat, we put the expression of summation of ei square divided by n minus 2 under root, because it's a standard deviation, whenever the variance of the disturbance term is unknown. And that is how we define the Z statistic. So this Z statistic is being done in order to define any kind of testing under the assumption that the population mean is represented by the sample mean, and thereby we can go for a better hypothesis testing. So by hypothesis testing, as it is said, that we have two types of hypothesis, null and alternative. And given the one-tailed test or the two-tailed test, we want to claim whether the sample estimate, which is beta star or beta hat, is significantly different from the population parameter, which is beta 2. And in this way, the testing can be done. So we go for a two-tailed test or a one-tailed test, and we want to claim that whether this beta hat lies within the interval of the standard error of the beta 2 or it lies within alpha by 2. So as we can see that here we are observing a confidence interval for beta 2 is being decided. So this confidence interval says that beta 2, which is the population parameter, which is basically the slope coefficient of the regression model, is lying in between the left-hand distribution or the right-hand distribution at alpha by 2 level of significance. So this goes back to the issue of either accepting or rejecting the null hypothesis. It is said that if the beta 2 lies in this region, which means that it is lying within this two lower bound and the upper bound, then the finding is statistically insignificant, which means that we are accepting the null hypothesis. But if it is outside this interval, either on the extreme corners, as it is seen less than minus alpha by 2 or more than plus alpha by 2, then the alternative hypothesis is being accepted. So this basically gets into a very important expression for confidence interval in terms of the regression coefficient under the classical linear regression model. So by regression coefficient, we mean that we have the probability, which is PR, where we find out that beta hat is basically being considered to be the lower bound, which is at minus of t alpha by 2, and thereby we have beta 2 as the estimated value of the coefficient. Again, we have the beta hat 2 on the right hand side. So that means both of them we are considering the beta to lie with 95% level of confidence, which means for 95% of the cases, it can be claimed that the population parameter beta 2 lies in between these two bounds. And that is how we can reject the null hypothesis and accept the alternative hypothesis. So whenever we go for a tabular representation of hypothesis testing, we go for some kind of decision rules. So given that the variance of the disturbance term is unknown, so whenever we say variance of the disturbance term is unknown, then we go for the two tail, right hand tail or left tail. As we follow in a normal testing procedure, we have the H naught. So for the two tail distribution, we always say that beta 2 is equal to beta 2 star, which means that the population parameter beta 2 will be equal to the sample distribution of the sample statistic beta 2 star, which is estimated from the sample, against H1, which is not equal to it, which means that we are inviting two cases which can be greater than or less than, and depending on that, the decision rule is being mentioned. So as per the decision rule, we say that the computed value of the t statistic must be greater than t alpha by 2. So this alpha by 2 will arise if in the null hypothesis we have equality sign, because it is making 0.25 level of significance. But when we go for the right hand tail, we observe that it is on the less than type and the alternative hypothesis is on the greater than type, which means that here we are only considering either the right hand side or the left hand side of the distribution. So if we look at the right hand side of the distribution, then t is greater than t alpha. That means if the computed value of the t is greater than t alpha, where alpha is taken up because it is not considered to be divided by 2 because one side of the distribution is considered, then we reject the null hypothesis. Similarly, we can see that if we operate on the left hand side of the tail, the same problem comes in where t is less than minus t alpha by 2. So given this table, we can see that a z statistic or a t statistic can be constructed whenever the variance of the disturbance term is unknown with degrees of freedom n minus 2, and we can basically make a similar kind of conclusions whether we accept the null hypothesis or we reject the null hypothesis. And that is how we can decide upon this particular claim in a context of a linear regression model. Here we introduce the confidence interval for sigma hat square u. Now this sigma hat square u is basically the estimated value of the variance of the disturbance term. As we know that sigma square u can be known or unknown, but depending upon the sample observations, we estimate sigma square u and we get sigma hat square u. So in order to define a testing of hypothesis for the random term or the disturbance term, we have to go for a non-parametric distribution. So till date, the discussion was only on a symmetric or a parametric distribution where underlying distribution was normal. That is how we go for z or the t distribution. But here we make a departure. So we go for a new distribution which is called chi-square distribution. So as we introduce this chi-square distribution, we can see that chi-square distribution follows n minus 2 degrees of freedom, because in a two-variable regression model, alpha and beta are the unknown parameters which are to be estimated. So by the formula of degrees of freedom, we have number of observations minus the number of parameters to be estimated. So this goes back to this expression of n minus 2 multiplied by sigma hat square u by sigma square u. So this sigma hat square u is basically estimated from the sample, and this sigma square u is basically the population variance. So just in case of a z statistic, we want to claim whether x bar is closer to mu or different from mu. Here also we go for a proportional analysis or a ratio analysis. We want to claim whether the sigma hat square u is significantly different from sigma square u or not. And that is how we define the chi-square test procedure. So whenever we are making any testing of hypothesis for the variance of a disturbance term, we always go for a chi-square distribution, which happens to be a non-parametric distribution. So this goes back to the confidence interval for sigma hat square u. So whenever we are building this confidence interval for sigma hat square u, we go for the confidence limits. That is what we decide. So here we observe that the first step refers to a limit which is within the probability levels of chi square 1 minus alpha by 2. This alpha by 2 at 0.025 level of significance. This chi square n minus 2 is lying within between the interval, just like the z statistic, and it is on the other side of the distribution, which is equal to 1 minus alpha. So in the first step, we observe 1 minus alpha to come up as 95% level of significance. Now in the step 2, we are basically substituting the expression of chi square n minus 2, which is given by n minus 2 sigma hat square u divided by sigma hat square u. That means we find out that in the middle part of this chi square, we have substituted the expression, and then what we have done, other things are unchanged, and that also lies within the upper bound and the lower bound. The upper bound is defined by chi square alpha by 2, which is on the positive side or on the right hand side of the distribution, and the lower bound is given by 1 minus alpha by 2. So it cannot be written minus alpha by 2 because sum of probability is 1. So since it's a non-symmetric distribution, we write 1 minus alpha by 2, or it's a non-parametric distribution also. Now we go for the final step, or the step 3. So in the step 3, what we do, we multiply n minus 2 and sigma square hat on both the sides, and then we keep only sigma square u in the middle, because this is the population variance. So this population variance is basically unknown, and that should lie within the confidence interval. So if it lies within this confidence interval, always we go for accepting the null hypothesis, which means that there is no significant difference between the population variance and the sample variance, or otherwise if it is less than or greater than, then we can reject the null hypothesis. So this is basically giving us 1 minus alpha into 100% confidence interval for the disturbance term, or for the variance of the disturbance term sigma square u. So this boils down to 3 particular cases. First we go for case 1. So our objective is significance of sigma square. We have done the significance of population mean, where we applied the Z test or the T test. Now we go for the significance of the population variance, which is sigma square. So under that, we go for the null hypothesis, which means that sigma square takes a particular value, which is sigma square 0, which is a specified value which the population variance takes. So automatically the alternative should be that it should be greater than this, because we will go for one-tail test or two-tail test accordingly. So this is with reference to the one-tail test, where we see that sigma square greater than sigma square O, or the specified value that we take. So what is the decision? The decision is very clear, that the null hypothesis is rejected if the computed value of the chi square, which means based on the statistic of the chi square, if we just compute the value and if it exceeds the table value at alpha n minus 2 degrees of freedom, this alpha is the level of significance, and since it's a one-tail test, we do not go for alpha by 2. We keep it alpha, comma, n minus 2, which is the degrees of freedom. So if this is the decision rule, then we can reject the null hypothesis and accept the alternative hypothesis that population variance is significantly different than the population parameter, which is sigma square 0 or sigma square O. Then we go for case 2. In case of case 2, we go for the other alternative, where the null hypothesis is the same, where the population variance is equal to a specified value of sigma square O, or 0. But alternative hypothesis says sigma square is less than sigma square 0, which means we want to operate on the left-hand side of the distribution. Here also we reject the null if the computed value of the chi square is less than chi square 1 minus alpha. So there are some important points to be noted in this particular slide. First of all, the sign is less than type because it is operating on the left hand side of the distribution. Secondly, it's not alpha, it's 1 minus alpha, because sum of the probability is equal to 1, and since it's not a symmetric distribution, we cannot do alpha by 2. We want to take 1 minus alpha, and that is what is considered to be as the level of significance. And n minus 2 is, as usual, the degrees of freedom. So in this particular decision rule, we can see that the computed value of the chi-square happens to be less than the table value of the chi-square at 1 minus alpha and n minus 2. And two important points to be noted, which is the departure here. First is regarding this sign, which must be in tune with the sign in the alternative hypothesis. So whatever sign we have mentioned in the alternative hypothesis, that has to be maintained here. And since it is on the left side, we are operating at 1 minus alpha, which happens to be a non-symmetric distribution. Now we open up for the two-tail test. So for the two-tail test, we write the null hypothesis as usual. That is, sigma square is equal to a specified value of sigma square O, but alternative is not equal to. So whenever we are regarding the not equal to type, there we have to be very careful about the point that we are inviting two cases together, either greater than or less than. So we go by the null hypothesis, which says that the chi-square computed value is greater than chi-square alpha by 2. So this alpha by 2 is basically the level of significance, which is because a two-tail distribution is being considered, comma n minus 2 is the degrees of freedom, and similarly we can go for less than type. But both the types have to be taken up into consideration when we go for sigma square not equal to sigma square O or 0. So that means in these three cases we have seen that if we are asked to find out the significance of the population variance under the testing of hypothesis procedure, first of all we need to find out whether the sigma square is known or unknown. If it is known, we take the sample variance, otherwise we continue with the population variance. But we should remember three types of settings are needed. Either the null hypothesis says that it is equal, or we go for less than type, greater than type, or not equal to type whenever we go for the testing for the disturbance term. Now we come up to the summary of all the discussions that we did in this particular module. So first of all, we have highlighted on the variance of the disturbance term. So the variance of the disturbance term is referred by sigma square u, which may be known or unknown. If it is unknown, we have to take it from the sample variance, which is denoted by small s. Secondly, when we go for the hypothesis testing of the disturbance term, because this will be implied in both whether we go for significance of mean or significance of variance. So in everywhere, in case of the mean, we have in the denominator the standard error. There this sample mean comes up or the sample variance comes up. And also when we go for the chi-square, there we have the ratio of population variance estimated as well as the sample variance which takes up. So when the variance is unknown, the sample variance comes up. So we have sigma square u, which is sigma hat square u, divided by sigma square u. And finally, we have elaborated on different cases of the testing of hypothesis. In all the three cases, we have invited for one-tail test or two-tail test. But the major point of departure is whether we are operating at alpha level of significance or alpha by 2 level of significance. So in this particular module, the variance of the disturbance term is taken care of, and accordingly the hypothesis testing is being done so that in any empirical exercise we can go for whether we are asked to find out the testing of the variance or the testing of the population mean, and accordingly we will apply t-test when we go for the testing of population mean, and we shall apply chi-square test when the population variance is to be estimated.